Hello all, welcome to my channel. In this subject of operational research, today I am going to explain the graphical method to solve a linear programming problem. So let's start with the graphical method or graphical solution to LPP. The first sum that I have selected is of maximization type. And it reads like this: maximize z is equal to 3x1 plus 4x2 subjected to x1 plus x2 is less than or equal to 450, 2x1 plus x2 is less than or equal to 650, and x1 x2 are greater than or equal to 0. So if you have seen my earlier video, you know that this maximize z is equal to 3x1 plus 4x2 is the objective function. The objective is to maximize what? The value of z, which is obtained by this decision variables x1 and x2. So we will solve this to find the value of x1 and x2 such that the objective is to maximize and we'll get maximum value of z. These are the two constraints. The first constraint is having inequality of less than or equal to type, and second constraint is also having inequality of less than or equal to type. And x1, x2 should be greater than or equal to 0. So when you are talking about graphical method, if x1, x2 both are greater than or equal to 0, means we are in the first quadrant. So our entire solution should lie in the first quadrant only. So let's start by solving this problem. Okay, the first step here now is to construct a table. What is a table and why would we construct a table? Now, in order to draw x1 plus x2 is less than or equal to 450, a line needs 2 points. These 2 points will be obtained from this table. Similarly, to draw a line 2x1 plus x2 is less than or equal to 600, we need 2 points, at least 2 points, which can be obtained by this table. So the first step would be to construct a table. Now you can see 3 columns, as I have already said. The first column will be the constraint itself. The second column would give us the first point, and the third column would give us the second point. Now, the first constraint is x1 plus x2 is less than or equal to 450. But I am interested in finding the value of x1 and x2. So what I will do, I will replace this less than or equal to by equal to sign. And I get first constraint as an equation, x1 plus x2 is equal to 450. Now if I put x1 is equal to 0, I will get x2 is equal to 450. So 0, 450 is the first point. And if I put x2 is equal to 0, then x1 will be equal to 450. So 450, 0 is the second point. So these 2 points, this one and this one, if I join these 2 points, I will get a line that is representing x1 plus x2 is equal to 450. Similarly, in order to obtain second line, which will represent 2x1 plus x2 is equal to 600, I will again put x1 is equal to 0 and x2 is equal to 0, so that I will get these 2 points. Okay, now we have obtained the 2 points and we can now draw the lines. So to draw the lines, the second step here is plot the graph. This is the first constraint, and considering the first constraint, I have this graph drawn. This horizontal line represents x1 and the vertical line represents x2. And this is a line which is obtained from these 2 points 0, 450 and 450, 0. This line represents x1 plus x2 equal to 450, but my constraint says that it is less than 450. So since it is less than 450, so you have to move towards the origin. And if you are moving towards the origin, this green region is the region which I am interested in, and not the region beyond this line to the right hand side of this line. This green region is the region, and every point in this green region would satisfy this instant x1 plus x2 is less than or equal to 450. Even the point on this line, the red color line, would also satisfy this constraint x1 plus x2 is less than or equal to 450. Okay, so we have drawn the first plot, then we'll draw the second plot. Here we have the second plot, which says that this line 2x1 plus x2 equal to 600 is drawn by this line. But our second constraint is Second constant is 2x1 plus x2 is less than or equal to 600. So since it is less than 600, it has to be towards the origin. This is the feasible region when we consider this 2x1 plus x2 is less than or equal to 600. It means that any point in this region, even the point on the line, would satisfy this constraint 2x1 plus x2 is less than or equal to 600. But then are we interested in each constraint individually, or we have to work together by considering both the constraints? Obviously, we have to work together by considering both the constraints. So what will be the next step? The next step would be to find the feasible region considering both the constraints. So let's find it. The feasible region by considering both the constraints. So first constraint says that this is the feasible region, this is the feasible region. But the second constraint says that no, this entire region cannot be feasible region. This part of the region and this part of the region is not feasible when we consider both the constraint together. If we consider any point here, this, it will satisfy the constraint number 2, but it will not satisfy constraint number 1. Whereas if we take any point here in this region, it will satisfy the constraint number 1, but it will not satisfy the constraint number 2. So we need a region where both the constraints would be satisfied, and that is this feasible region, which is obtained by this yellow color. This is the feasible region. Now every point in this feasible region will give us the value of z, and that value of z is accepted. But are we interested to find the value of z, or we are interested to find optimum value of z? Yes, correctly said. We are interested in finding the optimum value of z. And in this case, optimization is what? Minimization or maximization? Maximization. So we are interested in finding the maximum value of z. So our next step would be to find the maximum value of z. Now, before we move on to the next step, where will I get the maximum value of z? If I consider this point, suppose here the coordinates are 20, 20. I will get some value of z. I will put x1 is equal to 20, x2 is equal to 20, and will get the value of z. But if I move in this direction to maximize the value of x1, or if I move in this direction to maximize the value of x2, somewhere here is a point which is having better value than this point. Say 120, 180, this point is having better answer as compared to 2020. Or if I come here, this point may have better answer as compared to the earlier point. So we can move like this till the boundary. Now on the boundary, this boundary, we have better option as compared to the region inside the boundary. So although this is feasible region, this is not the optimal feasible region. Optimal feasible region is lying on the boundary. So now we are not interested now in this region, but we are interested only in this boundary, which will have feasible solution. Now if we think about this boundary, where exactly will be the feasible solution? Will it be here at this point? Or it can be here also, or it can be here also. It will go on increasing here value of z till the point where we get the corner point. So now we have again come to one more conclusion, that the first conclusion was this optimal region is not in this shaded region, it is on the boundary. Now second conclusion that we have made here is it is not on the boundary as well, it is only on the point where the boundary is changing its shape, that is only on the corner point, this corner point, this corner point, this corner point, and the fourth corner point. So our solution lies here on the corner points only and not on the boundary. So let's check. Now for that we have to find the objective function line. What is the objective function line? As we have obtained the line for two constraints, similarly we can obtain the line for the objective function. But then the objective function is z is equal to 3x1 plus 4x2. So we'll change the objective function in this way. 3x1 plus 4x2 is equal to some number. Now this some number can be anything such that I would be able to obtain the value of 2 points when I put 1 point equal to 0. For example, if I put x1 is equal to 0, I will be able to get x2 is equal to 120 divided by 4 is equal to 30. So I have selected in such a way that I am able to get this 30 number. Or if I put x2 is equal to 0, x2 is equal to 0, I will get 3x1 is equal to 120, that is x1 is equal to 40. This way I am able to get these 2 points. If I plot these 2 points here, these are here, and this is a line which is passing through the points 0, 30 and 40, 0. So this line is called as the objective function line. So as we move this line away and away from the origin, we will definitely get a point where the value of z is maximum. In order to do that, what will be the next step? Next step would be to move this line over this region. But we have seen that over this region, we will not get any point which is giving us the maximum value of z. Then we will move it over the boundaries. But also on the boundary, we will not get the point which will give us, will not get a point which will give us the maximum value of z. But then when what will we do? We'll move it over the corner points. This, and this. So on the corner point, we will get the maximum value of z. So move the line to the extreme corner. So we have moved that line from point O to point A. Here, this is the line. But then we still have a region, and this we are moving this line away from the origin in this direction. We see this next point is B here, and the next point here is C. Now we see that as if we compare B with C, B is here. I will say that this is the optimum value, but then we still have a region here where we can get an objective value, maximum or optimum objective value. So we'll move it from B to C. We have now understood that on B, it will not be the optimum value of Z or maximum value of Z, because there is still a region where we have a chance of getting better value of objective function than this point B or than any other point here. So we'll move it again to this point C. Now as this line is leaving the feasible region, there is only one point where it touches the shaded region, and that point is C. So this point C is the optimum value of Z, or this is the maximum value of Z for this case. So this way, by drawing the objective function line and moving it away from the origin, will give us only one point where it will touch before leaving the shaded region, and that point is called as the point of optimum value of Z. So this is one way of finding the value of Z. And what are the values? What is the value of Z here? X1 will be 0 and X2 would be 450. So X1 is 0, X2 is 450 is the value of X1 and X2. We put it in the objective function, we'll get the value of Z. So this is how we can find it graphically. Now how to find it by one more way, that is just by solving. So you can see this is the optimum solution. Now by solving, can we get the value of Z? Yes. Instead of moving this objective function line, there is another way by which we can get the value of Z, and that is to find the value of coordinates O, A, B and C. We'll do it like this. This is the objective function. This is the extreme point O. What are the coordinates? 0, 0. Substitute x1 is equal to 0, x2 is equal to 0, and we'll get z is equal to 0. Then move to the next point, that is A. What are the coordinates? X1 is 300, x2 is 0. So you put x1 is equal to 300, x2 is equal to 0, you will get the value of z as 900. We'll move to the third point, that is B, where x1 is equal to 150 and x2 is equal to 300. And here we will get z is equal to 1650. And we are left with the last point C, and here we'll put x1 is equal to 0, x2 is equal to 450, and we are getting 1800 as the value of z. So if you see here, we started from origin and we moved in the clockwise direction. We could have also moved in anti-clockwise direction, but we moved in clockwise direction. And if we move in clockwise direction, we can see that at every point we get a better value than the earlier point. At point A, the value is increased by 900. At point B, there is increase in the value as compared to the value of A. And at point C, this is the optimum value of Z. We cannot get a value of Z which is better than 1800. So this is the final value of Z. So I can say C gives us the optimum solution. C gives us the optimum solution with x1 is equal to 0 and x2 is equal to 450 and Z is equal to 1800. So either you find it this way or you move the objective function line. Both are going to give us the same result. In this case, Z is equal to 1800. So this is how every sum can be solved by graphical method. But there is one limitation to this graphical method, and the limitation is that we have x1 on this axis and x2 on this axis. What if we have x3? If we have x3, we cannot draw the graph. So the limitation is that this graphical method can be applied only when there are two and only two variables. There are only two variables at the max, x1 and x2. If we have third variable, then the graphical method cannot be used. There is no restriction on the number of constraints. In this case, we had two constraints. In the next sum, we'll see we have more than two constraints. But the constraint can be anything, in any number. But the decision variables can only be two. Then only we can use the graphical method. So we'll move on to the next method now, so that if there is some doubt remaining in this method, that will be cleared. Again, this problem is of maximization type, and this problem is, we'll solve this problem now. As usual, the first step is to construct a table. How many constraints we have? 1, 2, 3 and 4, and all the 4 constraints are less than or equal to type, and both x1 and x2 are greater than or equal to 0. So for 4 constraints, we'll get first, second, third, fourth. For 4 constraints, we now have points so that we can draw lines for this equation. X1 plus 2x2 is equal to 10. Using this 0, 5 and 10, 0 as points, we can draw line. Similarly for second, third and fourth constraint. Let us see how the line are drawn. So this is the first constraint. X1 plus x2 is equal to 10, and this is the line which is representing x1 plus x2 is equal to 10. But then we have less than or equal to 10. So the arrows will point towards the towards the origin, like this. So this is the first constraint, and this is the entire feasible region only for this constraint, only for this constraint. We'll move on to the second constraint. X1 plus x2 is less than or equal to 6. Less than or equal to 6 means pointing towards the origin, So we have these two constraints. Now if we try to merge these two constraints, we can see that this constraint does not go beyond 6, and this constraint is till 10. Means somewhere here, after this 6, this constraint is saying that no, this portion is not valid. So we'll first draw all the 4 constraints, and then we'll see which is valid. We have third constraint, x1 plus x2 is less than or equal to 2. Less than or equal to 2 means less than or equal to 2. 2 is this. This side we are more than 2, this side we are less than 2, because this is 3, 4, 5. So less than 2 towards the origin. So this is the shaded area. This is the shaded area. And for the fourth constraint, we have this as the shaded area. This area will not be considered because this gives x2 is equal to negative, x2 equal to negative, or non-negativity constraint says that x2 should be positive. So this small triangle which you can see, even though this line permits this small triangle, but then we will not consider this area. Now next what? We have got all the 4 constraints and we have got all the 4 plots for them. We'll merge all them and find the feasible region by agreement of all the 4 constraints. So the third step is to find the feasible region. First constraint says that this is the feasible region, which is shown by the green line, which is shown by the green shaded region. But second constraint says that you can include this portion, but then this portion has to be excluded. But then this is not accepted to the first constraint. So anyway, this region is not the part of our feasible solution. What has the second constraint done? The second constraint has reduced the feasible region. Now this portion is not the part of the feasible region. What does the third constraint says? It says that the feasible region can be here, not this, not this. This is accepted to first and second constraint, but not accepted to the third constraint. And the fourth constraint says that even this is not accepted. Even this small portion is not accepted. So if you consider the first, second, third, and fourth constraint all together, then from this point to 1, 1 to this point to this point, this point to this point, and from this 5 number point to 0. This is the area in this area which is bounded by this line. These lines is the shaded area. This one. So our final feasible solution lies in this. Feasible solution lies in this. But we are not interested in just a feasible solution. We are interested in optimal solution. So where would we get optimal solution? We would get it at this point, 1, this, or this point. So we'll name these points in the upcoming slides and see where exactly we get the optimum value of Z. Now, as I have told you, we have 2 methods. We'll follow the first method first and then the second method. The first method is find the objective function line. For that, we need to call the objective function. Here I have called the objective function and I have chosen a particular number 2. You can select 3, 4, 8, 10, 20, 100, anything. I have selected it such that I got the value of first point as 0, 2 and second point as 1, 0. Now, if the value of this is small, then you will get this objective function line close to origin. But if this value is bigger, suppose I take 200, then I will get the objective function line away from the origin. So I want it to be as close as possible to the origin so that I can move it from the origin outward. So I have selected as small as possible. This point is this 0, 2 and 1, 0, and I will draw the objective function line which looks like this. Now this objective function line, when it will leave the feasible region, the last point that it touches, will be the optimum value of Z. So let us move it starting from the origin. Okay, so it is, so we are starting with Z is equal to 0. Then we are moving to point A, where we are getting some value of Z with x1 is equal to 1 and x2 is equal to 2. Then we are moving to point B and the objective function line is here. It is still in the feasible region and it has not met the convex point. We'll move it further and here we can see that this is the point C where the line will touch when it leaves the feasible region. So this has to be the optimum value of Z, which is given by C. That is point is 4 and 2. We can roughly say it is x1 is 4 and x2 is 2. Still we'll move it to point D and point E and we'll check. Okay, no, it is coming into the feasible region for D and for E as well it is coming into the feasible region. So which is the final answer here? The final answer is given by point C. Let us calculate the values and check whether we are getting the same answer by the calculation. So this is the objective function. For point O, the coordinates are 0, 0 and objective function value is 0. For A point, the coordinates are x1 is 1, x2 is 0. So if I put x1 is equal to 1, I'll get 2 into 1 is 2. 2 plus this is 0. It equal to 2. For point B, I am getting coordinate 3 and 1, and this value is 7. For point C, we are getting the points 4 and 2, and we are getting the value as 10. So you can see that we started from 0 and we are slowly getting the optimum value of Z. But then when we come to point D, as we shift from point C to point D, the optimality has reduced. We are getting less optimum, we are getting value which is less than 10. So it is not the optimum value of Z. We have completed all the points, and now let us see which is the final optimum value of Z. Yes, it is given by C. So this is the optimum solution. So we have seen it by graphical method, and we have seen it by doing the calculations here. The optimum value of Z is 10, which is obtained from x1 is equal to 4, x2 is equal to 2. Substitute 4 and 2 for x1 and x2 here in the value of in the objective function, so that we will get the value of Z. So we complete our second sum here. Now let us move on to the third sum. Again, this is a maximization type of sum, and we may have how many constraints? 1, 2, 3, 4, and 5. We can see one difference here, that second constraint and fourth constraint are greater than or equal to type. Earlier we had less than or equal to type constraint only, and we have this fifth constraint which says that the value of x1 lies between 0 to 20. x1 is obviously greater than 0, but it is not more than 20. It has to be between 0 and 20 only. So we'll see how to solve this. First step, as usual, to construct a table. How many we have constraint? 1, 2, 3, and 4 constraint. So for 4 constraint, we'll get 4 lines: 1, 2, 3, and 4. Now, since second and third constraint says that there is no x1 here, so we'll get only 1 point, because it will be a straight line. x2 is equal to 3 and x2 is equal to 12. We'll plot the graph one by one. For the first constraint, the graph would look like this. This is the line which is representing x1 plus x2 is equal to 30. And since it is less than or equal to 0, it has to be towards the origin. Okay, second constraint, x2 should be greater than or equal to 3. So x2 is equal to 3 is this line. x2 is equal to 3 is this line. Now what it says, it should be greater than 3. If it is less than 3, it should be towards the origin, but it is greater than 3. Greater than 3 is above this, as you can see by the blue color region. So it has to be greater than 3 like this. What is the third constraint saying? The third constraint says that x2 should be less than or equal to 12. So where is this line? This is the line. But it is less than or equal to 12, means it should be below 12. As you can see, it should be below 12 here. And if you remember, we earlier had a constraint which says that x2 should be greater than 3. Means this region will not be the part of feasible region. Otherwise, it will violate the constraints. And the fourth constraint is saying that x1 and x2 should be greater than or equal to 0. So the objective, the constraint line will be like this. And since it is greater than or equal to 0, we have arrows like this towards. It should be greater than 0. So in this direction and not in this direction. And we have one more constraint which says that x1 should lie between 0 and 20. So x1 should lie between 0 and 20. x1 should be between 0 and 20, so in this direction only. So if I merge all the constraints, I will get this region. The first constraint which says x1 plus x2 should be less than 30. The second constraint which says that x2 should be greater than or equal to 3. The third constraint which says that x2 should be less than or equal to 12. So it is slowly reducing the feasible region. Fourth constraint, it says that x1 minus x2 should be greater than or equal to 0. And the last constraint, it says that x1 should lie between 0 and 20. So this is now the region which is left out of the entire region. This is the region which is left, and this region is the feasible region. And in this region only we will get the optimum value of z. Or rather, I will put it like this: in this region we will not get the value of z, we will get the value of z here. But that is bounded by this region. This region is bounded by the optimum value of z. Now the next point here is to find the objective function line. So we called the objective function. I chose 6 as the point here, and I get 2 points 0, 2 and 3, 0. I will plot the points here 0, 2 and 3, 0. This is the objective function line. Next step will be to move the objective function line to this corner points A, B, C, D and E, and see where it touches the last, at point B, at point C, at point D. So you can clearly see that D is the final answer. D is the final answer, and we'll do it by other method also. Here the objective function I have called. What are the coordinates of A? The coordinates of A are 3 and 3, and we get the value of objective function z is equal to 15 by substituting the value of x1 is equal to 3 and x2 is equal to 3. Then at point B, which is having coordinate 20 and 3, the objective function value is 49. So we are getting an improved value of objective function. At point C, we are still getting improved value of objective function. At point D, we are getting the value which is more than other values obtained at A, B and C. At E, we get a value which is less than the value of what we obtained at D. It means that at D, where x1 is equal to 18, x2 is equal to 12, will give us the optimum value of z. And this is the optimum solution where x1 is equal to 18, x2 is equal to 12, and z is equal to 72. We'll now move on to the fourth sum, and the fourth sum is on minimization type. So we'll quickly see what this sum is. If you have noticed here in the objective function, we have first time we have seen minus for this decision variable. So this decision variable is not minus. This decision variable coefficient is minus. So see, we have constructed a table here. 1, 2, 3. We have 3 constraints, and for 3 constraints we will get points like this. Once we get the points here, we can plot 1, 2 and 3 lines. We'll plot the lines. First, what it says that x1 plus 3x2 is less than or equal to 10. So this line is representing minus x1 plus 3x2 is equal to 10. But our constraint says that it should be less than or equal to 10. So this is the feasible region for constraint number 1. For constraint number 2, we have this region as the feasible region. This is the feasible region. And for constraint number 3, we have this region as the feasible region. So whether it is a maximization sum or a minimization sum, the constraint less than or equal to or greater than or equal to does not matter. Depending on what the constraint is, whether it is less than or equal to or greater than or equal to, we have to plot this feasible region. It does not depend on the objective function. Now next, if I consider all the 3 constraints, this is the first one, less than 10, second constraint less than 6, third constraint less than 2, I get this region which is the feasible region. It means that the answer will lie in this region. So what will be the answer? The answer will be obtained by these points A, B, C, D and E. We know the coordinates of point A, B, C, D and E since it is a graphical method. We can obtain the points and see we get the value of A is equal to 0, B is equal to -2, C is equal to 0. At D we are getting the value of Z is equal to 6, and at E we are getting the value of Z is equal to 20 by 3 is 6 point something. So which is the final answer? Yes, 20 by 3, that is 6.3 is not the final answer because this is not a maximization sum. This is the minimization sum. So only at the end when we are going to find the final answer, it matters whether it is a maximization or a minimization sum. Till that point, in the entire sum, we are not concerned with whether it is a maximization sum or a minimization sum. So E is equal to 20 by 3. At E, we get x1 is equal to 0 and x2 is equal to 10 by 3 and z is equal to 20 by 3. That is 6 point something is not the answer. But B, at B, where x1 is equal to 2 and x2 is equal to 0 and z is equal to minus 2 is the optimum solution. This is the optimum solution and our final answer. So someone may say that, okay, at this, since it's the minimization sum, I will get x1 is equal to 0, x2 is equal to 0, and this is the final answer. No, in that case, we will get z is equal to 0, but we have another solution which is better than that because it is a minimization sum. Now understand here that z value can be minus, but the decision variables are not negative. The decision variables are positive. The value of z can be negative because it is a minimization sum. Value of z can be negative, but these values should not be negative. We'll move on to the next sum, which is again a minimization sum. And what is the difference in this as compared to the earlier sum? All these three constraints are greater than or equal to type. So does it affects whether if it is a maximization or minimization sum, does this constraint affect it? No. The maximization or minimization comes in the end when we are deciding the value of z. So this is the sum where we have all the three constraints as greater than or equal to type. It means that the region will be away from the origin. So we construct the table and we get, for first line we get these 2 points, for second constraint we get this 2 points, and for third constraint we get these 2 points. So we'll plot this constraint. See now, 5x1 plus x2 is greater than or equal to 10. Greater than or equal to 10 means it will not lie in this region. Had it been less than or equal to 10, then this region would have been shaded. Since it is greater than or equal to 10, means it will move away from the origin. And this is the feasible region, which is shaded by the green line, green color. This. For the second constraint, okay, this is the second constraint, and it is saying that x1 plus x2 should be greater than or equal to 6. Greater than or equal to 6 means it should be in this direction, away from the origin. So we have it is away from the origin like this. What is the third constraint? The third constraint is saying that x1 plus 4x2 is greater than or equal to, if it is greater than or equal to 12, it will be away from the origin. Away from the origin means the arrows will point away from the origin like this. So if we integrate all these three constraints, we get this type of feasible region. This is the feasible region, and these are the corner points. This point, this point, this point, and this point. These are the corner points. So constraint number 1 says this. Constraint number 2 says this is the feasible region. Constraint number 3 says this is the feasible region. And considering all these regions, these are the points A, B, C, and D. And this is the objective function. We know the coordinates of A, B, C, D. We will substitute the coordinates here. A, we will substitute the values of x1, x2 for point A. In the objective function, we get z is equal to 36. At point B, we get z is equal to 16. At point C, we get z is equal to 13. And at point D, we get z is equal to 22. Since this is a minimization sum, the optimum solution is obtained by x1 is equal to 1, x2 is equal to 5, and z is equal to 13. This will give us the optimum solution. Now, since we have seen now the sums of maximization type and minimization type, and we have understood how to find a final solution, final value of z. we'll see something different which is called as multiple optimal solution. The name itself suggests that there will be more than one optimal solution. There will be more than one optimal solution. And for that, we have this question. Let us solve this. Now, our first step here would be to rearrange the problem. Why would we rearrange the problem? Because we can see the first constraint is x1 minus x2 is less than or equal to -1, which says that the right hand side value is negative. But the right hand side value should not be negative. That's why we change the constraint. How we change the constraint? We multiplied it by -1. So if I multiply this by -1, this will become minus x1. So minus x1 here. This minus and minus will become plus, so it will be plus x2. And this -1 will become -1 into -1, that is +1. And this inequality, which was less than or equal to type, will become greater than or equal to type. Now this constraint we have changed. We'll see this why we have changed this from -1 to +1. This in the next video, that is on various forms of a LP problem. Okay, so coming back here, first step is to construct the table. Okay, first constraint, second constraint, we got this and this as the points to draw this line represented by -x1 plus x2 is equal to 1, and we have 0, 2 and -4, 0 as 2 points represent in order to represent the constraint equation minus 0.5 x1 plus x2 is equal to 2. So let's draw them on the graph. Since this is less than or greater than or equal to 1, this is greater than or equal to 1, this will be towards this side, as you can see by the arrows. The second constraint, it is less than or equal to constraint, so the feasible region will be this. Now let us merge both the constraint. This is the first constraint and this is the second constraint. If you merge both the constraint, what we get here, we get this is the feasible region. This is the feasible region. So which are the corner points? This one, and this one. These are the only 3 corner points. And let us check by finding the objective function line. So this is the objective function given. We have selected here equal to 2. We obtained these 2 points, and let us now plot the objective function line. The objective function line is represented by this. And if as we move this line to the extreme points of the corner, what we see here, we see that this line, objective function line, is lying on the boundary of this, lying on the boundary. That is, it is lying on AC. The objective function line is lying on AC. So we are not able to get the final value of Z. Let us check it. Can we get it to the coordinates? Okay, so at point A, where we have x1 is equal to 2, x2 is equal to 3, we get Z is equal to 4. At point B, where we have x1 is equal to 0, x2 is equal to 1, we get Z is equal to 2. And at point C, where we have x1 is equal to 0, x2 is equal to 2, we get Z is equal to 4. So if you see here, x1 is equal to 2, x2 is equal to 3, we are getting Z is equal to 4. x1 is equal to 0, x2 is equal to 2, we are getting Z is equal to 4. So in both the cases, this and this, we are getting Z is equal to 4. So this A and C are giving us the optimal solution. They are giving us the optimal solution. So both these answers are giving us the same values. For example, this is the number of tables to be produced and this is the number of chairs to be produced. So if you produce 2 tables and 3 chairs, then also you will get the value of Z is equal to 4. Or if you produce 0 tables and 2 chairs, then also you are going to get the value of Z is equal to 4. And that was what was told to us by the objective function line, which was lying on this line AC. So it means that any point here on AC any point here on AC will give us the value of Z is equal to 4. For different values of x1 and x2 between A and C, we'll get the value of Z is equal to 4. So these are the optimal solution, and these are the multiple solution 1 and 2. Both the solutions are giving Z is equal to 4. So any point on this line AC will give us the value of Z is equal to 4. So this is the multiple optimal solution type of question where we will get multiple solution and all the solutions will be optimal solutions. Now we'll move on to see what exactly infeasible solution is. As the word suggests, solution is infeasible. It is not feasible. So if you remember in the earlier video, we have seen what do you mean by feasibility. And even in this video, I have told number of times what is the feasible region. So in this question, again, we have right hand side as negative. So we'll rearrange the problem. As we rearrange the problem, we will change the sign of this constraint. So this will become minus, plus, this will become plus, and this less than or equal to will become greater than or equal to. Next step is to create the table. So once we create the table, we have two constraints. So we have two lines, one for this constraint and second for this constraint. We'll draw this line. This is the line for first constraint, which is saying that it is less than or equal to 9. This is the line then for the second constraint, which is saying it is less than or equal to 2. This is greater than or equal to 2. This is a correction over here. So we see that constraint number 1 says that the feasible region lies below this line, and constraint number 2 says that the feasible region lies above this line. So this is the feasible region and this is the feasible region. So we are not getting any region where there is feasibility, where we can get feasibility. So we can say that the solution is infeasible. The constraint number 1 is saying that, oh, this is the feasible region, but the constraint number 2 is moving in this direction. So that we can conclude from this that the solution here is infeasible. And we will get infeasibility when such condition arises when constraints are mutually exclusive or inconsistent. Either the constraints are mutually exclusive or they are not consistent. It means that there is no unique or feasible solution to this problem. We can write the conclusion that this problem is infeasible. This cannot be a practical problem, and infeasibility is the result of wrong model formulation with conflicting constraints. The constraints are not properly formed, so the question itself is not proper. That's why we are getting infeasibility. And there is one more situation where we'll come across, that is called as unboundedness or unbounded solution. So we'll see this problem to understand what is unbounded solution. We'll construct the table. We know now how to construct the table. We have two lines. We'll mark the line. The first line is saying this. This should be less than or equal to 0. x1 plus x2 should be less than or equal to 0. So this is the region. Then second constraint says that 0.5 x1 plus x2 should be less than or equal to 1. So this should be the region. So if we merge first and second constraint, then we get this region. This is the first constraint which says that the region should be this entire region, and the second constraint says that the region should be this entire region, Now if you see here, we can increase the value of any one variable. And still this will not be violated. So let us move towards the question to see this. See, x1 plus x2 has to be greater than or equal to 0. Whatever value of x1 we select or whatever value of x2 we select, it will always, unless and until it is positive and it has to be positive, then this will always be greater than 0. So we can get infinite number of solutions. We can increase the value of x1 to anything, or we can increase the value of x2 to anything. and still this constraint will not be violated. Okay, so this is for this constraint. Now we'll see the second constraint. What does the second constraint says? Second constraint says that we can have any value of x1 and x2 such that this should be less than or equal to 1. So as long as, suppose we consider x2 is equal to 2, x2 is equal to 2 and x1 is equal to 0. So this will become 2, which is less than or equal to 1, and then it is violating the constraint. But if we consider any value of x1, suppose we consider x1 is equal to 50, then this will become 50 into 5, that is 0.5. So it is 25. So minus 25 plus whatever with the value of x2. Whatever with the value of x2. This is minus 25 plus 1. That will be 1. Minus 25 plus say 10. It will be negative. That is less than 1. So we understand here that if can I increase the value of x2 to after a certain limit? No, I cannot increase the value of x2 to after a certain limit. But I can increase the value of x1 to any limit. In this case also and in this case also. It means that x1 can take any value up to infinity. Now since x1 can take any value up to infinity, z can have any value up to infinity, and there is no binding to the value of x1. The only binding is x1 value should be greater than or equal to 0. Such a solution where there is no binding to the value of one of the decision variable or both the decision variable is called as unbounded solution. So you can say that here the solution is unbounded. So you can see here, as we increase the value of x1 and x2, or rather x1, the value of z can increase like anything. As we increase the value, z can increase like anything. And such a solution is called as unbounded solution. So unboundedness occurs when value of one of the constant can be increased indefinitely. Hence the objective function can increase indefinitely. It means that there is no binding to the value of objective function and there is no finite value of objective function. Infinity is the answer, and this happens without violating the feasibility condition. The entire region is the feasible region, and we can say that this is unbounded solution. So this explains the entire graphical solution to the linear programming problem. We'll meet in the next topic for different forms of linear programming problem.